In this lecture, we're going to look at a posteriori error estimates and the method of manufacture solutions. So this is the outline. We discussed that, well, there are some problems for which we have an exact solution, right? Those are great because then we can compute errors. But what if you don't have an exact solution? And actually, as we discussed multiple times already, if you're in 1D, the chances you get an exact solution are very high, right? One-dimensional problems are easy. But moving to 2D already makes things extremely complicated. So unless your domain has some special geometry and you can exploit symmetries and so the force is also, the load is also symmetric and this type of very, very simple configurations, then you can probably get an exact solution. But for the most part, you don't have an exact solution. So then if that is actually what you're going to be doing, so every time you grab a piece of software, you're going to model something and you don't have an exact solution. So how can you tell whether your solution is good or bad, right? You get some solution from your software, and how is it good? Is it any good at all? Can we get any convergence behavior? Well, you don't have an exact solution. So what we're going to learn today is how you can obtain an approximation of the exact strain energy, right? It is not going to be the exact value, but it's going to be a very good approximation, right? And so if you have that approximated quantity, then you can actually do convergence, and then you can see whether your finite element solution makes any sense. Then we're going to look at the method of manufacture solutions, right? And this is perhaps the most important, let's say, lecture in terms of your ability to have a properly verified implementation for your project, right? So in your project, I ask you, well, let's solve this problem with HFAM with a linear interpolation order. Then you move to a quadratic interpolation order. Then you have to implement PFAM, and PFAM all the way up to a kinetic polynomial interpolation order. So how do you test that the results that you're getting make sense? Well, this is what we're going to learn today, how we can test our implementations to make sure that whatever we code is correct. Again, if you take one thing from me, is that when we try to build complex pieces of software, we go incrementally, little by little. We create little pieces of code that are verified, right? Those are our building blocks. And so this is the way we move on to create complex behavior. And then we're going to look at some examples, right? So let's delve into the theory of posteriori error estimates, right? So if you recall the previous lecture, we looked at the bound for HFAM. And the bound, if you recall, was very tight for asymptotically. As our mesh size becomes very, very small, we can replace that inequality that we saw, was an upper bound, by just an equality. And so then, if you recall, we obtained the equation of a line in a log-log plot. So let's start with this a priori error estimate for HFAM. All right, well, we also know that the error in the energy norm can be written this way. If you recall, there is a little theorem in the book that basically explains how the error in the energy norm is simply taking the square root of the exact strain energy minus the approximated strain energy that is obtained from your numerical solution. All right, so we're going to call this whole thing just U, and this is going to be our UH. So H, again, just to denote that is coming from a finite element result. All right, H denotes, as we all know, the mesh size. So every time we see a superscript H, that is related already to the finite dimensional result, right? And the finite dimensional solution. Okay, so then if we just combine these two, right? And of course, we take the square root of that to remove that square root. Sorry, we take the square of that to remove that square root. Then we can write that U minus UH, which again is now the square of the error, right, can be written in this way. Now we have all those constants, right? We have C1. Remember that C1 was essentially a constant, right? So it was bounded by that constant. And then H is the mesh size. So the mesh size is something that we can know, right? Because obviously you're going to be solving the problem with a given mesh size. And beta h is our convergence rate, right? So we have this equation, and if you notice, this is also something that can be computed, right? Because obviously your finite element solution, we take 1/2 of U transpose KU, we get the approximated strain energy from the finite element solution, right? So now we have one equation, and how many unknowns we have? One. So clearly this is unknown. What else is unknown here?
C1 squared.
This is also unknown. And what else? Yeah, beta h, we know the theory is going to tell us something, but for a given problem, we don't really know beta h, right? Okay, so we have 3 unknowns and 1 equation. So what do you think we can do?
Make more equations.
We make more equations. How do we make more equations?
Solve the problem again.
We solve a problem again. Very straightforward, right? So if we have 3 equations, 3 unknowns, we need three equations to get rid of those, to be able to solve for the unknowns. So this is what we're going to do, right? So we're going to solve the problem with 3 different mesh sizes, H1, H2, and H3. And for each one of those mesh sizes, we're going to get a finite value of our strain energy, right? You have here UH0, UH1, UH2. So we can write those 3 equations very simply like that. And then we're going to start manipulating those equations. Let's see where we get, right? So if you take these 2, right? I'm just going to divide those 2 equations. I take the log. I take the log, of course, to take whatever in the exponent down, right? I get that expression here. Remember, I have divided those 2 equations, and so pretty much C1 squared goes away, right? Okay, and then I have this expression. So the natural log of U minus UH0 divided by U minus UH1 is equal to 2 beta H of the natural log of H0 divided by H1. Obviously, in this expression, these quantities here are all known. I still need to get rid of beta H. So now let's do the same. We take this equation here and that equation there. So we take those 2 and we do the same. And we get a similar expression, right? Now what I'm going to do is I'm going to keep manipulating those expressions. So if I basically divide those, I get rid of the beta H, the convergence rate, again, assuming that that can be done just because I am already in a regime where my convergence rate is not going to change. Remember, this is all based on the fact that we're using HFEM for a smooth problem, right? Then we divide these 2 equations, and notice what we have here, right? We have that the natural log of this whole expression that involves only known quantities, right? The strain energy for the 3 different meshes that we have, H0, H1, and H2. Those are the quantities that we compute from our finite element solution. Remember, we compute them by 1/2 U transpose KU, right? And then it's equal to this whole thing here on the right. And that whole thing is unknown or is known? Yeah, that is known. So all those are the quantities that I use to define my mesh sizes for the different problems. So that is essentially a constant. And we're going to call that constant Q. Right? That is something that can be computed. Okay? Well, then if we compute that Q, right, and we just take a look at this expression here, well, we can write it in this way. So notice that now all that manipulation leads to a single equation where the only unknown is U, right? That is the only thing I don't know in this expression. So Q can be computed because, of course, I do have the different mesh sizes I use to solve the different 3 problems, right? And then I have these guys here, which are basically the strain energy of my finite element solution. So the only thing that I don't know is U. But this is a complicated expression, right? It's actually a highly nonlinear expression in the unknown U. Do you happen to know any methods to solve nonlinear equations? Yeah, you can try to solve this expression numerically. There are different methods to do that, right? So you can have some golden ratio type of approach, bisection algorithm. There are many ways to solve nonlinear equations so that we can actually find U, and in the brightspace, I actually give you a piece of code that you can use readily to solve for the a posteriori error estimates in the project, so you don't have to code this yourself. I just give you that. It's a piece of Python code that you can use, okay? But now we can solve this equation, right, to obtain an approximation of the exact strain energy, right? Now, this is also working with the number of degrees of freedom. Again, just because if we assume that we have a uniform mesh, we can actually relate the mesh size with the number of degrees of freedom to the power of 1 over d. And again, the 1 over d goes there just because obviously the number of degrees of freedom is going to change with the dimensionality of the problem, right? And so you have two ways to compute that constant q. You can either use this way, right? Or you can use that way. In any case, that is going to be constant. And so now we can compute an exact or an approximation of the exact strain energy, right? So now the question is, well, it is an approximation, right? So how do you know you are happy with that approximation? Sorry? You can do convergence analysis and you see if things look like a theory predicts, then yeah, but if it doesn't look okay. And this is where most students stop, because they really don't go beyond and they are seeing something that doesn't make sense and they just don't do anything about it. But how can you know that the approximation of the exact strain energy is good enough?
It's constant when we refine the mesh even more.
Okay, that's a good suggestion. So let's just create one more discretization, right? Let's call it H3, and then let's try to get for that strain energy the same way we saw for U, right? And then we compare your new U with the old U, and if they are pretty much the same, then yeah, you can say that is good enough. If not, yeah, we can keep doing this procedure. Obviously, you would be taking the 3 most refined meshes to do this computation, right? Because those are, let's say, the more exact values of your so they get closer to the exact strain energy. All right, and in the book we looked many times at this problem of the pile in an elastic foundation. If you recall that we were pulling it, right? So we have an exact solution, and this is actually a nice example because it has an analytic solution, and so we are able to compute the exact solution, and so we can actually compare what we do when we solve the problem numerically and we try to approximate that exact strain energy. And here I'm just giving you an example. If I just use 3 different meshes to solve that problem, right? And then I can compute the strain energies for each one of those numerical results. And then when you actually compute the exact strain energy, right? The exact strain energy looks like this, and the algorithm, root finding algorithm, found that, which is essentially 0.06%. And notice that I am using all the significant digits, right? And well, we are engineers, and normally we don't do that, right? Like normally, if you express something with 16 digits of accuracy, it makes no sense. Well, except here things are making sense because we are really in a realm where error is so small that we really need to take into account as many digits as we can, right? And notice that in this particular case, the error is super small. And what you will see in the project is that, again, your error is going to be small, very small. So if you compute your a posteriori error estimate and it turns out that your approximated exact strain energy is remarkably different than the one that I give you, then something went wrong somewhere, okay? Okay, yeah?
Should the 3 discretizations we use always be the finest ones, or?
Yeah, that's what I would do. And again, that's because as you refine your mesh, you always want to use the 3 most refined ones because those are the ones that are getting closer to the exact energy. Yeah?
How do you do this with PFAM?
That is a great question. How do you do this with PFAM? Well, unfortunately, in this lecture, we are not going to look at how do we do this with PFAM, but I have not seen the theory developed for PFAM. right? Remember that again, we are assuming that this result is extrapolating from 3 solutions that we have. And it is, of course, assuming something, right? The main assumption is that our problem is smooth and it's being applied to HFM, right? So the solution that we get to solve, right, which is this very complicated solution, is really highly nonlinear. So I would assume that if we try to do the same for PFM and extrapolate a value for PFM, it would get even more nonlinear, and I have not seen the theory for that. Yeah? Okay.
Sorry, question.
Yeah.
You said you want 16 significant figures, like digits.
Yeah.
But if you're calculating to 0.06 relative error,
Yeah, I just chop off all the rest.
wouldn't you?
Yeah.
Wouldn't you go like into like what? 6
Yeah, I could also compute that number to 16 digits of accuracy, but that is something I don't care about at this point. I just want to show you that it is pretty much almost the same strain energy. Yeah, you have a question?
So I have a question about this method specifically. Does it work only for uniform measures?
Yeah.
So if we have like local elements concentration, then we can use it.
Yeah, exactly. It works with local uniform meshes everywhere. And so in the case you have a singularity, in which case you would actually change the mesh as you approach the singularity, yeah, this estimate would not work. Yeah? Okay. Now we move forward to something called the method of manufactured solutions, right? So this is actually a great mathematical tool that we can use to check our implementations. So what is exactly this? Essentially, we need to just create a problem for which we know the exact solution, right? So think about an exact solution that you want to solve for, and then the idea is that, well, when I plug the exact solution into my differential equation, then I get the source term or the force term, right? And then I can solve that numerically, and I can check whether I can actually recover the exact solution more or less that I assumed. So we create a problem such that the exact solution U belongs to some space, right? Now we plug it into the PDE. So in the case of elasticity, for instance, we have the divergence of the stress plus the body force. Now this is like our pseudo body force, right? Then we plug it here, and then obviously we can solve for what B tilde is, and now we solve the problem numerically with this body force, right? So we solve the discrete equation. Again, this is the abstract form of the Galerkin projection using finite element spaces, right? With boundary conditions, UH is equal to U bar on gamma D. Remember, gamma D was our Dirichlet boundary, and Cauchy's expression to relate the stresses to the tractions along the Newman boundary, right? Normally, it's better if we just have this. So Dirichlet boundary conditions are better, but this is also working with Newman boundary conditions. But obviously, this, right, has to come from this. So we have an exact solution, so we actually know what should be the value of the displacement or the traction along the boundary. And then once we obtain the numerical solution, we can see how close or far we are from the solution, right? Okay. And so let's try to apply this idea in a very simple problem. So in the project, I asked you, implement quadratic Lagrangian elements for our one-dimensional problem, right? So let's see how we can do that here. I'm pretty sure you're asking now why we didn't see this earlier. Well, because you can see in that way that it is challenging, very challenging, if we don't follow an approach that we're going to follow now with the method of manufactured solutions. So given a working linear finite element program, which is what you were given, implement and test a one-dimensional quadratic formulation with Lagrange elements, right? Which is what you guys did. So we all did this already. So you saw that the shape functions for our quadratic Lagrangian elements can be written in canonical space in this way, right? These are my Lagrangian elements, and of course they form a partition of unity, because if at some point I add those, they add up to 1. And of course, they have the Kronecker delta property because the functions is equal to 1 at their corresponding node and 0 at the other node, right? 1, 0, 0, and then 1, 0, 0. And so these are the derivatives on the side. And now that we have that, we choose an exact solution. So let's make things very, very simple. I'm going to assume that my exact solution is a quadratic function, right? Just as a first step to test my quadratic implementation. Because if my implementation is correct, right, and I assumed a quadratic exact solution, then my quadratic approximation should be exact. So I should have no error. There should be no error. And that is the way we're going to trust our implementation. If I get some error or I see that the solution is not exact, then something went wrong. I have to debug it, right? So again, we assume that. What do we do now with the method of manufacture solution? We assume already the form of U. What do we do it? Where do we plug it? In the differential equation. So we plug it into the differential equation. For now, let's assume EA is equal to 1 so that we don't have to deal with this axial rigidity, right? We plug it here, and then we solve for our body force. We do this analytically. It's a piece of cake. We just have to apply the derivative twice of this function. We change the sign. And it turns out that for a quadratic, all we need to do is to apply a constant value of the force per unit length equal to 2 for that particular shape, right? And so we do that, and now we solve the equation. We're going to solve one element, only one element, right? Because, well, with one element, I have enough information to see whether my implementation is correct. Notice that the exact solution that I chose, right, is equal to 0 where? Well, I want it to be equal to 0 at the boundaries, but which are the boundaries? 0 and 1. And so this function is going to be equal to 0 at x equals 0 or at x equals 1. And so that is essentially the domain I need to choose. And so my element is going to be my physical element, right, in physical space. Remember that my canonical element is always between -1 and 1, but my physical element is going to be between 0 and 1, right? So I'm going to solve, that's why these integrals are bounded this way. So I am basically solving between 0 and 1, right? With boundary conditions, and again, I am applying a Dirichlet boundary condition here. UH of 0 is equal to UH at 1 equal to 0. Very, very straightforward. So I do this with one element. And then this is so simple to do by hand that I show it to you by hand here. You don't necessarily have to do it. Actually, in fact, most times where you apply the method of manufacture solution, you're never going to do it by hand, right? But this is so simple that we can show it by hand. And so in that element, my element freedom table is 1, 2, 3. Those are the nodes my element is connected to. The field can be written in this fashion, right? We have UH. So these are the three shape functions, and those U1, U2, and U3 are the degrees of freedom associated with the shape functions. And now we, of course, to get the stiffness matrix, we need the strain displacement matrix. So we take the derivatives of that, right? Yeah, and there is an error here because this should be not X, this should be C. Yeah, and so when we plug that back into our stiffness matrix, we get this whole expression. And if you recall, since we want the strain displacement matrix, which is the derivative of the shape function vector with respect to X, and we had the mapping, we're using an isoparametric formulation, then we have to apply the change rule, right? And the reason for this J squared that shows up in the denominator is because this guy here is supposed to be d phi dx, but d phi dx is d phi dx, dx dx. So that's why you have 1 over the Jacobian. And so here you have this ratio of the Jacobian divided by the Jacobian square, right? And well, when you carry out the computation, this is the final stiffness matrix for your element. But I wanted to point out something here, and this is something that we discussed also last Friday. So we're using an isoparametric formulation, and yet the Jacobian is actually constant, right? You can show that the Jacobian is simple simply the length of the element divided by 2, which is exactly the same as the Jacobian of the linear interpolant, right? The linear interpolation. And the reason for that is that, well, when you write the Jacobian, it turns out that you can write it like this. And for the choice of the middle node exactly at the center of the element, this whole expression here that is multiplied by c goes away. That is equal to 0. And so we get LE divided by 2, which is the same Jacobian that we have for our linear interpolation, right? That is why when you actually use the same code, we get the same Jacobian we were using for the linear interpolation. Yeah? Okay, so now that I have the stiffness matrix, I compute the force vector. And again, if you recall, my B was equal to 2. And so now this is the shape function vector, right? My domain of integration, I always work in the canonical element space. And so it's minus 1 to 1. And then I have the Jacobian here. Well, it turns out that this computation leads to that force vector, right? So now I have my local force stiffness matrix, which happens to be my global stiffness matrix because I don't need to do any assembly, right? And I have my global force vector also computed in with one element. Yeah, so now that we have both, what do we do? Well, we solve the system, right? And for that, we need to apply boundary conditions. So my entire system can be written like this, right? And in fact, because I prescribe the 2 of the degrees of freedom, I have 3 degrees of freedom problem. So essentially, we're solving for a single degree of freedom problem, which is super easy, right? And so let's solve this problem. So what do we do normally when we solve the problem? How do we apply the boundary conditions? Yeah, we zero out. So we take those. Let's simplify that 3 away, and then we zero out the rows and the columns of the first degree of freedom. And then, well, we set that equal to 0. So we essentially transform the first equation into a trivial equation of the form 1 multiplied by u1 is equal to 0, right? And then we zero out the rows and columns of the third degree of freedom, right, which is all the way to the left. So all of this is 0, 0, and then I apply equal to 1 here, and I transform that third equation of a trivial equation of the form 1 multiplied by u3 equal to 0, right? And well, the solution at the middle node is simply that 1 over 4. And then we implement this and we check, right? Obviously, I show it to you by hand because it's a very simple problem, but normally you code it and then you should be able to get u2 is equal to 1/4 exactly. Otherwise, we did something wrong, right? And then we can obtain also the exact strain energy because, again, this is a quadratic problem, so the analytical solution is a quadratic, so my approximated strain energy should be exact. So if we take that 1/2 u2 k22 u2, we get a strain energy of 1/6. And then, well, if you actually compute that analytically using the expression for the strain energy in the integral 0, 1, you get 1/6. And now we know that our solution is exact, right? And now we know that if we get that in the code, we are confident in that at least up to that point our code is correct, right? So what do? We make a test. We make sure that that test never fails, otherwise we broke the code somewhere. And we move on to the next method of manufacture solution, to the next manufacture solution. Then we test, for instance, another polynomial interpolation. But let's discuss what are the things that we can do, right? So, of course, once we verify our code, we make it robust. So what can we do now that we solve the problem with one element? Use 2 elements to test assembly, right? Obviously, if I'm going to take the same problem and I want to test for 2 elements, right? Now my elements are not going to go from 0 to 1, but let's say we take 2 elements. So now obviously the domain size doesn't have to change, otherwise I'm changing the problem that I'm solving. So my first element would be from 0 to 0.5, right? So I would have the first node at 0, the second node at 0.25, the third node at 0.5, then there is a fourth node at 0.75, and then the last node at 1, right? And then this way, I should be able to test the assembly procedure to see whether I can assemble the local stiffness matrix in the right locations in my global stiffness matrix. Well, if that works, chances are it's still going to work for more elements. So you try more elements. You divide that by, I don't know, 10 elements or whatever number of elements you want. You should still get the same exact strain energy. Then you can change so that the element is not equal to 1 anymore. So, sorry. You can also change the exact solution, right? So you can in the beginning, we tested this, right? The length of the element. But you can also change the problem, right? So that your solution doesn't go, let's say, from 0 to 1. That's what I meant with this expression. It's actually not accurate. I have to change it. But the idea is that you can also change for, let's say, let's make the first element and solve with one element, but let's make it twice as large, right? So then we are no longer testing the assumption that our original element length was equal to 1. So you can test for that as well. Then we change the axial rigidity. In the beginning, we assumed that I was equal to 1. So let's say now it's going to be equal to 2, right? So then our body force, remember that when I obtain the exact solution, is going to be 1 divided by E divided by A. So now my body force is not equal to 2. It's going to be equal to 1, right? So then we change the EA, and then now we can test our formulation, our implementation, to see whether it works for a different axial rigidity. And like this, we can keep building complexity. And then, for instance, we manufacture another problem whose exact solution is not quadratic to carry out convergence. So now that I have a quadratic implementation, if I try to solve for a problem for which the solution is not quadratic, then I can do convergence analysis, right? And then I can see the slope. In this first problem, there is no slope. Why there is no slope? No, it's zero error, right? There is no slope, so I cannot really check for the rate of convergence. Right? So if I want to see how my quadratic implementation actually works for a smooth problem, well, I have to solve for a problem for which the quadratic doesn't give you the exact solution, obviously, right? So we would manufacture a solution of a high order or some trigonometric solution, for instance, like the one I showed you earlier, this nice sinusoidal function. And then you can compare the convergence rates that you get with the theoretical values. And if your problem is smooth and you're not getting the actual, what would be the convergence rate for this case, for a quadratic implementation? Given by the theory, the a priori error estimate should be 2. Again, assuming that you are computing that convergence rate as a function of h, the mesh size, it should give you 2, right? Because the convergence rate was the polynomial interpolation order. If I do the same but with the number of degrees of freedom, it should be? No. 2 as well. Thank you so much, right? Because even though when I plotted the error as a function of the number of degrees of freedom, right, the negative slope of that curve, right, had beta h divided by d, but in this case d, the dimensionality of problem is still 1, so I should get the same convergence rate, right? And then we move on. What else we can do? Let's say implement a test file so that from now on the quadratic implementation does not break when you change the code, test-based development, and then now we move to a cubic formulation. So what do we do with a cubic formulation? What do you do first? Yeah, okay, we implement our cubic shape functions. If, let's say, we're using our Lagrangian element, if we implemented a PFEM, the functions are not going to change, right? They are the same. Yeah? So, cubic formulation. What problem will you solve? One element, but what is the exact solution? Cubic. So you go for a cubic, right? And then you can check your implementation for a cubic. You compute the exact strain energy very simply using Mathematica, or analytically you can do it by hand, right? You compute your exact strain energy, and now we have the numerical solution, if I'm using cubic polynomials, should be exact. It's the same thing. We should have no error. And then we move on. And this is the way we build our software. And so this is exactly the way you should try your PFEM implementation, right? So what most people do, all right? What most students are going to do always, they are going to implement the PFEM somehow, and they are going to try to see how it performs in the problem that I gave you. What is the problem with that approach?
Might break for other problems.
Huh?
It might break for other problems.
No. What is the main problem with that?
If the solution is not correct, you don't know where to look.
Yeah, exactly. You don't know where say there is a bug somewhere. How do you tell there is a bug? Say that for whatever reason the bug is not so nasty, but it gives you something that makes sense, but it's still not correct, right? You will never be able to find that you have an error. And that is a problem with that approach. And most students do that, unfortunately. Why? Well, because implementing the method manufacturer solution takes a little bit more energy, right? And we are all looking for the principle of minimum potential energy, right? All right. When develop our programs, we develop our programs incrementally. And these have to change. Another. We start with small, well-tested building blocks and progressively increase the complexity of the code. This is something that, again, we talked over and over. And if you take something from this entire course, should beat this, okay? This is what we do in computational mechanics. And sometimes, yeah, sometimes we spend a month, 2 months, 6 months tracking a bug, and things don't work. So we try to see, we think hard, right? We try to figure out where the issue is. We run out of ideas. At some point, we start dreaming about solutions. I have found solutions to several problems while dreaming, which is next thing you know, sometimes you wake up and you have to write it down, otherwise you are gonna forget in the morning. That's insane. These things happen, right? Sometimes you spend months tracking a bug, and then suddenly you realize, oh, I can do this. I can make this test. I simplify the problem to the simplest geometry that shows the bug. And then you can test more forcefully. And then you discover the bug. You fix it, and things work. And that sensation is what I guess keeps pushing us into computational mechanics work for years, right? Because that sensation of ecstasy is like unique. Anyways. Huh? Yeah, it sounds like madness in this, indeed. Well, are there any questions regarding this? So now you guys are all prepared to test your implementations, to see if it works, and to basically have, by Friday, the implementation of PFEM. Someone sent me an email. Who sent me an email? Alberto. Where is Alberto? No, not here. Okay. All right, guys. We stop here. We see each other on Friday, and let's try to have PFEM working by Friday, as we discussed. Yeah? Promise?
We'll see.